Have you ever looked at a modern car and wondered how it can be so lightweight but also incredibly strong? Well, a lot of the time, the secret is joining materials that honestly have no business being together, like aluminum and steel. So today, we're going to pull back the curtain on the amazing science of how engineers fuse the absolutely unfusible.
Okay, so let's just dive right in. I mean, on the surface, it sounds pretty simple, doesn't it? You just melt them together. But in the real world, this is one of the biggest headaches in material science. And the reason why, it's because these materials at their core have totally different personalities.
Seriously, think of it like a clash of the titans. In one corner, you've got aluminum. It's light, it's flexible, and it melts at a pretty chill 660 degrees Celsius. But in the other corner, you have steel, super strong, rigid, and it won't even start to melt until you hit almost 1400 degrees. So when you try to force them together with heat, they don't cooperate. They create an atomic battleground right where they meet.
And that conflict, well, it brings us right to the heart of the problem. We're about to unmask a villain that's so small you can't even see it, but it's sabotaging our joints from the inside out.
Okay, imagine you're trying to glue two strong pieces of wood together, but the glue itself dries into this super fragile glass-like film. What's going to happen? It's going to snap, right? That is exactly what happens here. This brittle layer forms right at the boundary, and it is the #1 reason these kinds of joints fail.
And this troublemaker has a name: intermetallic compounds, or IMCs for short. Now, these aren't some nice, smooth blend of the two metals. No, they're entirely new crystal-like structures. And because their atoms are locked into this super rigid grid, they have zero flexibility. They can't bend, they can't stretch, they just break. So you get the picture. These things are the bad guys. If we ever want to create a strong, reliable bond between different materials, our first mission is crystal clear. We have to figure out a way to defeat, or at the very least, outsmart these microscopic villains. The big question is, how?
All right, on to our first solution. This is where scientists get to play the role of peacemaker. Instead of just forcing these two warring materials together, they introduce a diplomat, a third party that can kind of speak both of their languages. The strategy here is it's so elegant. Engineers take a super thin foil of a more agreeable metal, like copper or zinc, and they sandwich it right between the two main materials. This inner layer acts like a buffer zone, a translator. It stops those nasty, brittle IMCs from forming, and instead it actually encourages the materials to create new compounds that are way stronger.
And the results? Oh, they speak for themselves. In one study, by just adding a simple zinc inner layer when joining copper and titanium, researchers saw the joint's strength leap up by over 33%. That little zinc diplomat basically negotiated a much stronger peace treaty at the atomic level. It's incredible. And here's another really cool example. When you're working with aluminum and magnesium, putting a copper interlayer in there doesn't just block the bad reactions, it actively redirects them. It's like a chemical GPS telling the atoms, hey, don't go down that brittle road, take this other route instead to form stronger compounds.
But, diplomacy isn't always enough. Sometimes you need to bring in the muscle. So the next strategy we're going to look at involves mixing in microscopic super soldiers right into the weld itself to toughen the whole thing up from the inside.
And believe me, there's a whole army of these tiny titans to choose from. You've got things called high-entropy alloys, which are basically complex metal cocktails for when things get really hot. You've got nanoparticles like carbon nanotubes to make the structure tighter and stronger, and you can even add tiny sheets of graphene to help the joint carry a heavier load.
Now, one of the most clever ways these nanoparticles work is through a process called Orowin strengthening. Just try to picture the inside of the metal like a bunch of perfectly straight rows. When you put stress on it, tiny defects can slide along those rows, and that's what leads to a break. Well, these nanoparticles act like microscopic roadblocks, pinning those defects right where they are so they can't move. It makes the whole structure way, way stronger.
And the big question is, does it work? Oh yeah, it works. Look at this. By reinforcing an aluminum weld with carbon nanotubes, scientists got a joint that had over 92% of the strength of the original solid material. That is ridiculously close to a perfect weld. So we have our diplomatic inner layers, and we have our tiny titan reinforcements. But the last piece of this puzzle isn't a what, it's a how. The actual process, the way you apply the heat, the pressure, everything else, is just as critical as the materials you use.
Just look at this comparison. It's night and day. A standard weld gives you that thick, flat, weak IMC layer we talked about. But by adding high-frequency ultrasonic vibrations while you're welding, you totally shatter that brittle layer. It gets broken up into this thin, wavy, serrated shape that acts like a microscopic zipper, interlocking the two materials and making the bond a whopping 43% stronger.
And get this, the job isn't even over when the welding stops. What you do after the fact can be a total game changer. Gently heating the joint afterwards can boost its strength by 22%. That's pretty good. But flash freezing it with a cryogenic treatment, that increases the strength by a massive 54%. Okay, so we've been deep in the microscopic weeds with the diplomats, super soldiers, and all these advanced techniques. Let's zoom out for a second and connect all this incredible science to the world that we actually live in. Why does any of this really matter? The big takeaway here is that there's no single magic bullet for this. Creating these amazing joints requires a really deep understanding of the whole picture. Picking the right base materials, choosing the right diplomatic inner layer, adding the right reinforcements, and having precise control over the entire process. It is a true balancing act.
And why do we go through all this trouble? Because this science is what lets us build lighter, more fuel-efficient cars. It's what allows us to make smaller, more powerful electronics. It's how we build aerospace parts that can survive the extremes of space. This isn't just theory in a lab. This is the hidden engineering that is building our future.
You know, this quote from the research paper just sums it all up perfectly. The future of making things stronger, lighter, and better really all comes down to mastering and tailoring these tiny features at a scale that you can't even see with your own eyes. Which, of course, leaves us with one last really exciting question to chew on. We are getting better and better at this every single day. So, what happens when there are no more unjoinable materials? What could we build then? It's pretty amazing to think about.